Hey, hello and welcome to our video demonstration of quantitative analysis of vinegar via titration. What you're doing today, you're carrying out a procedure known as a titration, and you're carrying that procedure out so that you can determine the molarity of acetic acid in a solution of household vinegar. If you didn't know, vinegar is just a solution of water and a chemical known as acetic acid. So to do this, you're going to carry out a titration. A titration is a classical form of chemical analysis where you're measuring the molarity or the concentration of one chemical against a known concentration in a different chemical. So you have one chemical where you know the concentration, you know its molarity, you react it with the other chemical to determine its molarity. Before you do the vinegar titration, though, first you have to determine the concentration of sodium hydroxide that you're going to be working with. We'll be using sodium hydroxide today, and the first thing we have to do, part A of the experiment, is standardizing the sodium hydroxide that we're going to use. So we'll know that molarity of that sodium hydroxide. Before we get on with that, though, a little safety note. Sodium hydroxide is one of the more common laboratory reagents you'll encounter. It's common household lye. That said, it's a wee bit dangerous. You might see our graphic here. This is your eye. This is your eye on sodium hydroxide. It can blind you in a matter of minutes if it gets in your eye. So one of the most important features today, safety-wise, is throughout the day, since you're working with this sodium hydroxide, keep your goggles intact. If you get sodium hydroxide on your skin, you'll feel it getting kind of slippery. It's how you notice that a little bit got on your skin. If you're wondering why is it getting slippery, it's quite literally turning your skin into soap. The way you make household soap would be sodium hydroxide and animal fat. Put them together, you have soap. So this stuff can turn you into a big pile of soap. If it gets on your skin and it's slippery, don't freak out, just wash it off. It washes off quite easily. So that's our sodium hydroxide. First thing you have to do in this procedure, you have to mix up a rather dilute solution of the hydroxide. We have 6 molar sodium hydroxide here, and in the first step of the procedure, they ask you to take 25 milliliters of the strong stuff here. I'll take 25 milliliters of my strong sodium hydroxide. 25. 25.0 actually. Pour it into a large container. And then dilute it up with water. Now I'm going to use this to rinse out any little last traces of that sodium hydroxide from my graduated cylinder. And then dilute it with, I believe it's 475 milliliters of water, más o menos. That's my concentrated or 6 molar sodium hydroxide. This will be my nice dilute solution of sodium hydroxide. And we have to know the precise molarity up to four significant figures. To determine this molarity, we're going to do part A of the experiment, which is the standardization. When a solution is standardized, it simply means we know the molarity to several significant figures. Now, to standardize this, the theory behind it, we're going to measure the concentration of this chemical, our sodium hydroxide, by reacting it with a different chemical, potassium hydrogen phthalate. No, you won't be tested on how to pronounce potassium hydrogen phthalate, but you better be able to spell it. Just joking. Okay. Potassium hydrogen phthalate, which is abbreviated KHP, is this chemical. It's a weak acid. It's available in a nice, solid, highly purified crystalline form. so it's easy to handle. So we can take KHP and weigh out a precise amount of it. I have my KHP weighed out here. I know exactly how much it weighs. Happen to know the molar mass of KHP. It's 204.22 grams per mole. And since I know the exact mass of it, I weighed it out. I know its molar mass. I'll be able to calculate how many moles of this acid are going into the reaction. If you look at the stoichiometry of this reaction, you notice 1 mole of the acid reacts with 1 mole of the sodium hydroxide. So if I can calculate moles of KHP, I know how many moles of sodium hydroxide were used. If I know the moles of sodium hydroxide, and I also carefully measure the volume of sodium hydroxide, I can find the molarity, because molarity, of course, is moles divided by liters. So I'll take that moles of sodium hydroxide divided by the volume in liters. That's how I get to the molarity. We'll show you the procedure in a moment. A little later in the video, we'll show you how to actually do the calculations. So, to do a titration, you typically use an instrument called a burette. This is a standard burette you'll find in most laboratories. Important thing to notice about it, the valve. Like most valves in chemistry, when the valve is parallel to the pipe, things can flow. When the valve is cutting across, it's off. Most important thing to know about a burette, when you're filling it, when you're pouring stuff in, make sure it's off. We've all done it before where it's on, you're pouring stuff in, and it's just not filling up because it's dribbling all over your leg. But none of you are going to do that today because this is just a demo. So, you start with your burette off, and what a burette does for you. You read it from the top down, it gives you a fairly accurate measure of volume to 2 decimal places, so it's to 1/100th of a milliliter. So if you know the initial volume, you know the final volume, you have those 2 numbers, subtract, that tells you the exact volume that was delivered from the tip of the burette. Now, handling a burette, filling them up, different ways to fill burettes. Some people will use funnels. I do not recommend that. If you try to fill with a funnel, your burette will end up being full, your funnel will be full, and you'll make a mess. I've always found that the easiest way to fill a burette is by pouring your sodium hydroxide into these little plastic flasks. So here's our dilute. Again, it's the dilute sodium hydroxide that we're working with. You pour it into here. Don't try to fill it by doing this, you'll just spill it. So take the burette out of the stand, and you can easily pour. Now, one thing you do with titrations, you never just fill it up and start doing your titrations. You first want to condition your burette. That means you've rinsed it through with the stuff you're about to fill it with. So we have a waste container here. We'll drain that little bit out. Ideally, you do this 2 or 3 times. That way you assure that the only thing in the burette is this. So if some previous student left a few drops of water in there, that's not affecting your experiment. You rinse it out with the stuff you're filling it with, and again, that's referred to as conditioning the burette. So we'll pretend I've done that 3 times. To fill it, again, make sure the burette is off, and you simply pour. Now my burette's filled up, ready to go. One common mistake people make when they first start doing titrations, they want to always start at 0. Absolutely no need to start at 0. Just start somewhere near the top. You take the initial reading, so you'll know the initial volume. Drain it down till you want it. You know that final volume. The total volume that came out of the burette is the final minus the initial. There's absolutely no need to start at 0. So our burette's ready to roll. Here I've weighed out my KHP carefully to several decimal places. You want quantitative transfer of this standard acid into your flask. Now, obviously, that didn't get all of it, so you rinse your little weigh boat out and make sure that every last little speck of that KHP, that standard acid, gets washed into the flask. Now, KHP takes a little bit of time to dissolve, so to help it out, you can just let it sit there for a long time, or you can just gently heat it over a low flame. Like that. You just gently warm it up. It doesn't take too much heat, and that KHP will go into solution. You don't want to boil the solution. You just want to warm it up enough so that your KHP, and again, that's potassium hydrogen phthalate. KHP is not potassium hydrogen phosphorus. We use a terrible abbreviation for it. All the bottles of it you see are going to say KHP, but it's potassium hydrogen phthalate. And it has this lower mass. And now that stuff should dissolve pretty quickly. In order for this to work well, it helps to add a little bit more water. The only purpose of adding more water here is it gives you a good enough volume for it to stir up. We're going to use a little stir rod in here, and you see how that stirs the solution for me. Turn that down a bit. Now, what we're going to do is we're going to add the sodium hydroxide to it until all of that acid has been neutralized. There's a certain amount of acid in here right now. After I add a little sodium hydroxide, there's less acid. Still less acid. Eventually I'll get to a point where there's no acid left in here, and at that point the solution should turn pink like that. It's going to turn pink because we're adding a couple drops of an indicator called phenolphthalein. Again, the spelling will be on the test. Just kidding. Just kidding. So, a couple of drops of phenolphthalein. And since we're looking for a light pink colored endpoint, it's always handy to put a piece of white paper or something underneath the flask. I will do that so we'll be able to see the transition to the pink color a little bit more effectively. Set this all up here. There we go. Now, as I start to add the sodium hydroxide, that's a base. The KHP here is an acid. Acids and bases react with each other, they neutralize each other. So as I add the sodium hydroxide, it's going to begin to destroy the sodium hydroxide. The sodium hydroxide is going to begin destroying that potassium hydrogen phthalate. Initially, nothing happens. The solution is staying acidic because I have a lot of KHP here. It's a little bit less KHP here now than there was a moment ago, still less. Do you see how it's developing that little bit of pink? That's because locally in the solution there's an excess of the hydroxide, and as soon as there's an excess of this hydroxide, it turns pink. Right now, excess of KHP, the acid. So keep adding it. I'm getting close to what is called the end point. The end point is where adding one additional drop of the sodium hydroxide makes it turn pink. That's your end point. I'm getting close to it. There's different ways to proceed at this point. Some people, so they don't shoot past the end point, will do this. They'll flick their wrist, and you figure every time you do that, you've added about 1/10 of a milliliter or less. And right there, that's my end point. It went from being colorless to pink. The best endpoint is a light pink, a probably went just a little bit past the endpoint there. So, you take the initial reading, the final reading, that's the total volume of sodium hydroxide that was used. And again, I know moles of KHP because I weighed it. So I can calculate moles of KHP, which is equal to moles of sodium hydroxide. So I know how many moles of sodium hydroxide were contained in this volume. And again, moles divided by liters will give you the precise molarity of that sodium hydroxide solution. Back to our titration experiment. Now, once you have the data, it'll go on your report sheet like this. Again, we'll give you the data on a PDF. You'll just have to do the calculations. That report sheet's going to have 3 pieces of data. The mass of the KHP, the initial reading on the burette, and the final reading on the burette. So how do you fill this thing out? Well, based on the mass of the KHP, you can find moles of KHP. We've got that calculation set up for you over. So, you know the exact mass of the KHP. The molar mass we use here as a conversion factor. You see how grams of KHP cancels out. And you do the calculation, you'll find you get 6.846. 6.846 times 10 to the negative third moles of KHP. That's not there. Okay, so we have the moles of KHP we just calculated. The next line on the report sheet's asking for moles of sodium hydroxide. Well, you might recall the stoichiometry in that reaction is 1 mole of sodium hydroxide for every 1 mole of KHP. So this number is simply going to be 6.846 times 10 to the negative third moles. That's telling me how many moles of sodium hydroxide came out of that burette during the procedure. Now, the volume of the sodium hydroxide, the whole idea of measuring with the burette, if we take the difference between these two numbers, take the 23.98, we subtract out the 0.12, we'll get 23.86 milliliters. That's the volume of sodium hydroxide that came out of the burette. And the key feature here is we can now say this many moles of sodium hydroxide were contained in this volume of sodium hydroxide. Changing milliliters into liters, changing into liters simply means divide this one by 1,000. That will give us 0.02386 liters. So this many liters of sodium hydroxide contained this many moles. The molarity of the sodium hydroxide is what we're after, and it's simply going to be this many moles, this number, divided by this many liters, this number. Pause. Okay, so again, what we're after in this whole procedure, the reason we're doing the standardization, is we want to know the molarity of the sodium hydroxide, the molarity of this solution. We know the moles, we know the liters. Simply divide moles by liters, and you have the molarity. Now, molarity of the sodium hydroxide, you could write it like this. You may notice on the report sheet it's written this way. Just put square brackets there. Throughout chemistry, if you see a chemical in square brackets, that usually means the molarity of it. In Chem 2, you'll see that notation quite a bit. Rather than say the molarity, they'll just take the stuff and put brackets around it. But doing that calculation, we now know the molarity of our sodium hydroxide to be 0.2869 molar. Okay, for completing your lab report, You may notice we're sending you 3 sets of data, trial 1, trial 2, trial 3. When you're doing titrations, that's pretty typical. You do 3 or 4 trials to find the molarity of something, and then you take the average of them, and that's the molarity of it. Take the average. Typically you do multiple trials. If your data is all very close, you get 0.2869, 0.2867, 0.2865, you're doing a good job. If your data is all over the board, you're getting 0.2869, 0.350 molar, you've got a problem. That's why you always do multiple trials, to see if indeed you're getting consistent data. Okay, folks, now on to part B of the experiment. Remember, the whole goal is to find the exact molarity of acetic acid in household vinegar. The way that's going to work, now that we know the molarity of sodium hydroxide from part A, we're going to react that sodium hydroxide with our vinegar, and our vinegar is just a solution of this chemical, acetic acid. And like all acid-base reactions, the acid and the base get together, they react to make water and the corresponding salt. So what we'll do is we'll measure a precise amount of the vinegar solution. We have some of the vinegar in a beaker here. We have a 10 milliliter volumetric pipette, and we're going to put 10.00 milliliters of the vinegar into our titration flask. If you're not familiar with the volumetric pipettes, there's a little line etched in them somewhere. They're all over the place. They're individually calibrated, so one might have the line here, another one might have the line up here. We use these little pumps to bring the vinegar level just a little bit above the line, and then you want to drain it down to the line, some way above there. I'll bring it down till it's right on the line, and then I'm going to drain it into my flask. The proper way to drain it into the flask, you hit the little button here and it begins to drain. And at the very end, there's always a question: do you push the extra vinegar out? How do you deal with it? I'll show you in just a moment. The correct way to use a volumetric pipette like this, once you got a little bit left in the tip of the pipette, you touch it to the bottom of the flask. There's still a little bit left here, but that has transferred 10.00 milliliters of the vinegar to the flask. So now I'm fairly confident I have 10.00 milliliters of the vinegar solution in here. Now we're going to move on to the titration part and figure out how many moles of the acetic acid are contained in there. For the titration, again, you have to add a couple drops of the phenolphthalein, so this will make the solution turn pink once all of the acid has been neutralized. Helps to add a little bit of extra water so that it stirs nicely. Again, the water does not affect the total amount of acid that's in there, so that's not a huge issue. We add the stir bar. Add our stir bar. Put a little piece of white paper under there. Grab our burette with the sodium hydroxide. And what you want to do here is you take the initial reading from the burette, so you know the initial volume, and you start titrating. You keep adding the sodium hydroxide until it turns pink. And again, that's referred to as the end point. So let me get out of the way here so you can see it. Well, if I lift up the paper, you might be able to see it turn pink a little better. So you keep adding that sodium hydroxide. It's destroying the acetic acid. Eventually you'll run out of acetic acid and it should turn pink. It should turn pink. It should turn pink. What did you fill this burette with? We're getting there. We're getting there. We're getting up on the end point. There we go. You're starting to see a little bit of pink color. At that point, you slow down. And you want to get it to where one drop of the sodium hydroxide makes all the difference between colorless and pink. So, closer and closer. Closer and closer. I'm almost there. Some people at this point will use the drop-by-drop method where they just adjust the burette to go one drop at a time. We're definitely sneaking up on that end point. We're almost there. I bet you one last little, not quite. Hopefully you get the idea. You want to get to where one drop makes a difference between colorless and pink. Okay guys, the second report sheet you have to complete is for part B here, where you calculate the molarity of acetic acid in the vinegar. The report sheet looks like this, and the actual numbers you get, we're only going to give you a few numbers. It's of course the molarity of the sodium hydroxide from part A, the volume of the vinegar, 10.00 milliliters, because remember, we measured it with that volumetric pipette. You'll have the initial and the final volumes of the burette, and you have to complete these calculations that I'm going to go into right now. Hey guys, so for part B, you'll have data that will look like this. You have the molarity of the sodium hydroxide from part A, the volume of the vinegar that we measured with the volumetric pipette, the initial and the final volume of the vinegar. To complete this lab report, it's pretty easy to get to the volume of sodium hydroxide, the difference between the two numbers. So if you do subtraction, 25.82 minus 0.65, you'll end up with 25.17 milliliters. That's the volume of sodium hydroxide that came out of the burette. Now, converting that into liters, of course, gives us 0.02517 liters. Now, moles of sodium hydroxide. One of the more fundamental conversions you have to learn in chemistry is getting to moles if you're given a volume. You're given a volume here. You're given a molarity here. You've got to take those two numbers and turn them into moles. So it's a simple matter of looking at this molarity as a conversion factor. That 0.2877 means 0.2877 moles of sodium hydroxide per 1 liter of solution. So this is your conversion factor. It lets you convert liters into moles, or if you flipped it upside down, moles into liters. So to get to moles here, we'll take our 0.02517 liters times our 0.2877 moles per liter. Doing the math there, you all see how liters cancel out. If you do the math, you end up with 7.241 times 10 to the negative third moles. So down here, our moles of sodium hydroxide is that 7.24. That's how many moles of sodium hydroxide came out of the burette. That also is the moles of acetic acid that were in the flask, because it's, again, 1-to-1 stoichiometry. Okay guys, we calculated the moles of sodium hydroxide that came out of the burette. Turns out moles of sodium hydroxide equal moles of acetic acid. The ultimate goal here is, what's the molarity of the acetic acid in the vinegar? Again, molarity is moles divided by liters. Hey, we know this upper number. we know the number for moles. It's the 7.241 times 10 to the negative third moles. That much acetic acid was dissolved in what volume of vinegar? Oh, 10 milliliters of vinegar. 10 milliliters is, of course, 0.01000 liters. So the molarity of the acetic acid in that vinegar is going to be this number divided by this, and that's going to give us 0.7241 molar. So that would be the molarity of the acetic acid in the vinegar. And that concludes this part of our discussion. Okay guys, the very last part of this report sheet, page 194, it wants you to take the molarity of the acetic acid that you found and convert it to a mass percent. So you'll be filling out this part of the report sheet. In the discussion of the experiment, it should show you how to do that. Now, if you're wondering, ballpark, what's that mass percent? Well, here's a label of the vinegar solution, and you might notice right there it says adjusted to 5% acidity. In other words, this solution, the vinegar, is 5% acetic acid by mass. So when you complete this part here, you should be coming in the ballpark of 5% when you complete this sheet. And that's our demonstration of this week's experiment.